Okay, this is exercise 4, so slightly trickier again. Again, we've got striking and dipping beds, but this time we've got two different directions that they're dipping in. So over here we have ones that are dipping towards the west. You can see the little tick mark is pointing towards the west. Over here we have ones that are dipping back towards the east, like we had before. And you got this symbol here, which is a fold symbol. So here we've got folded strata rather than simply tilted strata like we had in exercise 3. So it's a good habit with your maps when you see these fold axes to draw in the fold axial trace, which in this case is running north-south. So it's a good idea just to trace that in. This little symbol here, these arrows pointing away, that indicates that we have an anticline. A syncline is pointed back like that. So ultimately these arrows are pointing in the direction that the beds are dipping on either side of that fold. So for those who can't remember, this is an anticline, this is a syncline. So I remember it because anticlines look like an A, synclines look like the Y in syncline. So here we're dealing with an anticline, we can tell because of that symbol, but you could also tell simply through the strikes and the dips of the beds on either side of that fold. So we've got this repetition of strata going on. We've got this unit, which I think is a sandstone. I can't remember exactly what the key is, but it looks like a sandstone. Fairly standard sort of symbols that we're using here. Dotted patterns is normally sandstone. This will be a limestone. This will be a shale, and then this will be something like a conglomerate. Then we repeat it, but going the other way. So now we have conglomerate, shale, limestone, sandstone. So that's how we know that we've got folded strata. Not only do we have things dipping in the opposite direction, but we've also got this repetition of strata, which you need to have this symmetry on either side of the fold to identify it as a fold. If you had completely different rock units over here, it wouldn't be a fold, it would be something else. It might be something like an angular unconformity that we're dealing with. But in this case, we're dealing with a fold, which we can tell because of both the dipping of those beds, but also because of that repetition of the strata. So this is the cross section that I produced from this. Fairly similar process to what we did before. Again, we've got flat topography, so that's the first thing we draw on. So we're not worrying too much about topography in this practical. You should have figured out how to do topography from the first exercise, but most of these other ones have flat topography. Once you get into the case study map, however, you'll realize that you have to deal with topography as well. So we've drawn on our topography. Then we've gone back, we've taken our piece of paper, lined it up from A to B again. So we've got our piece of paper lining up along here. You'll notice that once again we're dealing with rocks we're dealing with a cross-section line that is perpendicular to our strike lines. That's a 90-degree angle there, so we don't have to worry about a Woolnough diagram for this particular exercise. So we've lined up our piece of paper, you put your markings along it where each of those unit boundaries are, and then you transfer that information onto your cross section. So you've got your little unit boundaries sitting along here. So you draw that on, and now you have to put on the dip information. So, on this map we can see that these ones are dipping towards the west. On this side they're dipping towards the east, and they're dipping at 40 degrees on both sides of that fold, just in different directions. So that angle in there from the horizontal, that would be 40 degrees, 40 degrees, and over this side 40 degrees, but now towards the east rather than towards the west. So again, remembering on our cross section that's west, and that is east. So once you've done that, you take your protractor, you measure down this. Again, do these as hand-drawn lines. Don't use a ruler. Geology very rarely will form perfectly straight lines. Try and get it as accurately as possible. You should be careful, precise, and accurate, but you don't need to rule the lines. The main thing that I want you guys to be doing is making sure that you're keeping the units the same thickness. Now the reason I'm saying don't rule the lines is because we've simplified it a little bit here by having everything at 40 degrees, 40 degrees. That's pretty common on a real geological map. You'll see some that say 45, some might say 50, some might say 35, and some might say 40. So then how do we deal with this? And the problem is if you then go and measure it with a ruler and say this one's at 35 degrees, this one's at 50 degrees, or something like that. And then you have different angles, and if you take your ruler and go down like this, that one's going shallow and this one's going quite steep, and all of a sudden the rock unit actually ends up intersecting each other, and that's actually not something that's geologically reasonable. What you want to do is make sure that these units maintain the same thickness throughout. So if you have things that are dipping at slightly different angles, and that's a very common situation. There are both geological reasons why that might occur and simply measurement reasons. If you're using a compass, it's generally only accurate to plus or minus about 5 degrees. So you've got measurement errors to consider as well as geological variation to consider. So what you really, more realistic, is trying to keep these units relatively same thickness. So if this one's at 35 degrees and this one's at 50 degrees, you have to fudge it just a little bit. You're not really making it up, but you're fudging it, trying to keep those thicknesses the same thickness rather than having this as a ruled line directly at 35 degrees down and this one as a ruled line directly at 50 degrees down. So I don't want to see rulers, I want to see these being hand drawn. So you're trying to keep this thickness, that's the important thing, trying to keep this thickness the same throughout that unit. So you can see that I've kept that pretty much exactly the same throughout each of these units. Even though these are hand drawn, they're not ruled lines. So that's what I really want you guys to do. I don't want to see units that go and blow out at depth like that, and I don't want to see units that end up joining up to themselves like that, because that's not a geologically reasonable situation. Okay, so we've drawn our lines in at 40 degrees, down like that. The next thing you do, once you got all your units in, drawn in, down like that, like that, is you should always draw in, make a habit of this once again, draw in your fold axial plane. That's what this line is here. The fold axial plane goes through the hinge of the fold. It's marked on our maps. This is that fold axial, this is where the fold axial plane is here. So when it's on a map, we call it the fold axial trace. That's the trace along the map that the fold axial plane makes. It's a line along the map, and it's going through the hinge of the fold. So this is where it's curving around, and we've shown that here. That's an important piece of structural information. All folds should always have a fold axial plane drawn on it. Sometimes you'll see it abbreviated as a FAP. That's a fold axial plane. And again, draw the symbol on it so that we can see that this is clearly an anticline. And the next thing you should do is you really should try and dash what's happening above the ground. Now these rocks have now been removed, so they're obviously not there anymore, so you don't draw them as a solid line, but you draw a dashed line just to show what the structure is doing above the ground. And this just helps somebody come along and interpret exactly what the structure is doing. So it's a good idea to just dash those units above the ground to show how they would have been prior to that erosional event that has removed all of this material. So that's what would have happened. And again, you can see up here, we're always trying to keep that unit thickness exactly the same as we go around that fold. And again, it's very rare, once again, with our ruled lines, if we have a perfectly ruled straight line up like this, and then down the other side. That's a very rare looking fold. There are folds that sometimes have this distinctive bend in them, this triangular sort of shape, but generally, most folds I've seen are curved around. So you actually, if we had gone and taken a strike and dip right here on this fold axial trace, we'd actually find that the beds here are horizontal, just in this particular location. And that's because that's where it bends around. If you look right here, if we measure our bedding right here, it's actually horizontal right where it kinks around, and that's part of the fold. So it's very common to see that within these folded strata. And the last thing to remember is, once again, we don't actually know what's happening at depth below this unit. We don't know how thick this unit is because we don't have the information. So I've simply drawn question marks, a line with question marks around down here. We actually don't know what's happening at depth in this particular case. So unlike some of those earlier maps where we could predict what was happening at depth, here we really can't. So I'll just put question marks there just to remind us that that is the limit of our information. So basically down here, this is Here Be Dragons territory. It's like the old maps you used to see where they hadn't charted the whole world yet. They had Here Be Dragons. Yeah, alright. Well, I'll leave it there. I guess the last thing to remember is that you should have a key and a scale on all of these maps. There, make sure you have your key, your scale, your title, and your AB, and all the labels on all of these maps. So I'll move on to the next exercise now.